So, welcome to today's class. Yeah, I think our numbers have thinned a little bit. I don't know, probably people are just watching it online or not quite sure what, or maybe because everybody's still trying to get their homework in order. So the deadline is the end of the class. If you email it, make sure you email it to the email address for the homework by the end of the class. And yeah, there are no extensions. But obviously, if you screw one up, you can basically drop one of the 5 homeworks. So I think that's a fair balance. Okay. Now, are there any questions with regard to last Monday's class? Okay. If you have questions, ask the TAs, or come to the office hours. I think you have something like 9 hours of office hours total for this course, right? So it's 1 office hour per TA, plus 2 hours from Barnabash and 2 hours from me, except that I won't be around next week. So overall, I think there should be more than plenty of time for you to ask questions should something not be clear, or just post it on the forums and somebody will reply. Now, let me have a quick vote. So we can do 2 different things today. We can, after we finish up on novelty detection, we can go into a fair amount of detail on regularization. And so that'll be mathematical, looking at differential operators, smoothness of functions, and so on. And it'll basically get to the point why kernels work as well as they do. Okay. So that's one thing, and if you like function analysis, you might enjoy this quite a bit. The other direction is to look a bit more at practical things, for instance, how to do spam filters and how to compress function classes into a very compact space. So if you're going to use these algorithms on large data sets, the latter might be more useful. So if you're more of a practical bent, you will probably enjoy that more. Both parts are in the set of slides, and Barnabash is probably going to cover some of the regularization as it fits in his class. So who wants to hear how to do things in a compressed, hashed way, basically the more practical part? Okay, so that's like 6, 7, 8 hands up. Okay. Who wants to hear regularization theory and function analysis? Wow, I would have expected it to go exactly the other way around. Okay, good. So don't complain if it's math today. And yeah. Okay, wow, that's quite surprising. Good. So we basically looked at single class SVMs on Monday. And what we did is we basically said, well, let's find those points. And here's the origin, and we want to have a hyperplane, so this is the normal vector, that is as far away from the origin as possible, and at the same time, separates all those points from the origin. So in other words, what we wanted is that w dot x was greater or equal than, let's say, 1 minus psi I, so this was with the slacks, and well, we basically had in the objective function 1/2 norm of w squared plus c times sum over I psi I. And then we said, well, actually, this is maybe a little bit of a problem, because if this hyperplane could move, then maybe I could, have a predefined number of novel observations, right? By just making the problem easier or harder, I'll get a certain fraction of points. And that's quite often useful, for instance, if you have a network intrusion detection system, then you don't want to overwhelm the sysadmin with ridiculous numbers of items. Instead of that, you'd probably want to have something that will be able to say, well, okay, here are the 10 most suspicious things. I mean, it's just like when you use a search engine and you search for machine learning, you don't necessarily want to find out that there's an insane amount of stuff on machine learning on the internet. You just want to get maybe the 10 most relevant things and then move on. So the trick was then to actually turn this 1 into some margin rho. Okay, thanks goodness I have horrible handwriting. And then, of course, we want to make this margin large, so we would take minus nu times m times rho. And then somehow we lost this coefficient c, but you can actually check that you can get rid of this coefficient c without any loss of generality, because you can always hide that parameterization in nu. That may or may not be an assignment today. So in any case, what we got is we got a quadratic program, and we had some alpha i's being basically the dual program. We had the alpha i's being in that interval between 0 and 1, and also we had the constraint sum over I, alpha I equals m times nu. And that already told us that there must be something about the number of points that sit on the margin or that are on the wrong side. Now, I wanted to show you also from a primal space optimization point of view how you can derive this new property, which is basically that on average you're going to get something like nu times m points that are on the margin or on the wrong side. And so this is kind of useful, because effectively this gives us some insight also on what's happening in the dual problem, and there are versions of that problem also for classification. For classification, sometimes it might be quite useful if you can just say, well, set me the parameter in such a way that maybe I see something like 5% error. Well, why would you care about that? Because if you have some prior knowledge on how hard or easy the problem is, you can just set nu to that level of hardness, and you'll get a fairly decent estimate as a result out of it. Okay, so let's just see what happens here. Let's group our points into m plus, m0, and m minus. So m plus are basically all those points here. They're m plus. These points over there are the m minus, and the points exactly on the margins are the m zeros. Right? So basically m pluses are those points which are perfectly classified anyway. So now let's see what happens. Suppose we solve the optimization problem, and at optimality, well, let's just say we change rho to rho plus delta. Okay? And obviously, since we're at optimality, we have to assume that that objective here does not really change as, well, that can only go up as we increase rho to rho plus delta. Well, what happens is, if we increase rho, so the margin moves this way, that basically we pay m minus plus m0, because all those points in the boundary now also pay that penalty, right? These are exactly contributions from the soy i's. But then we gain something, okay, so times delta. And we gain something because this now gets larger, so we get minus nu times m times delta. So dividing out delta here, and of course this has to be less than 0, so, sorry, it has to be greater than 0, otherwise, well, it doesn't get worse. So what we get is that basically we get that m minus plus m0 is greater, equal than nu times m, right? Because basically, if I move delta this way, then I get this. Now, if we decrease things by delta, so in other words, if rho goes into rho minus delta, then what happens is, so in other words, this guy goes over here, then those points exactly on the boundary don't really benefit from it. So I just have that m minus times delta. That's by how much this now decreases. But then I pay a penalty because I've actually increased rho. So I have this plus nu times m times delta. Okay, but this is also greater equal than 0, right? Because if it were less than 0, then I could immediately improve the solution of my optimization problem just by making rho smaller. So again, we throw out delta, and what I get is that nu times m is greater or equal than m minus. So in summary, what we get is that m minus plus m0 is greater or equal than nu times m is greater or equal than m minus. So in other words, except for those points on the boundary, nu times m tells you essentially the number of support points. So you can do the very same reasoning for regression. You can do the very same reasoning for classification. And yeah, that's basically another couple of lines. Or you can just look at the dual problem, you'd see it from the dual. Okay. Any questions on that so far? Okay, so this is, as said, the new trick. And don't ask how much time we spent on thinking about the name of the variable relative to the algorithm. Okay, good. That's the theorem. The last part is that then the fraction of points exactly on the boundary vanishes eventually, because what happens is that this hyperplane is a set of measure 0, so if the complexity of your function class doesn't increase too drastically with the sample size, then the probability of finding a hyperplane that actually contains a non-negligible number of points goes to 0. Okay, this is a small toy example, and so you can see what happens as you play with nu. And so this is always the same data set. If you make the so in these two cases you can see that it's essentially the same set of observations regardless of whether I have some additional points here or not. So these are considered outliers. But if I decrease the bandwidth of my kernel, so I allow for less smooth functions, then I'll try fitting this and that. And then if I, on the other hand, keep a wide kernel, but I just have a different threshold, it'll just end up throwing more points away. Anyway, so this is kind of an intuition. Here, as you can see, you basically get a lot uglier digits. The other nice thing is that if you set nu equals 1, well, recall that this is what we get here, right? Sum of alpha I equals m times nu. So for nu equals 1, what follows is, so can somebody tell me what the values of the alpha i's have to be if nu equals 1? I have this constraint, sum over the alpha I going from 1, m, is m times nu. What's the value for the alpha i's if nu equals 1? 1, correct. Good answer. So now what I therefore get is that my function f of x, which is w dot phi of x, just happens to be sum over I, alpha I, k of xi and x, which, well, in the case of nu equals 1, we have sum over I, k of xi and x. Now this is exactly what we got from Parson Windows. So that's kind of nice to see that at least a classical technique for novelty detection comes out as a special case. Basically, and this is, if you recall, also in our thresholding setting where I said, well, we don't really care about densities at the high density peaks, so we don't really care about this part. If I move this up high enough, I'll end up caring about all the peaks, so I'll end up modeling the entire density. So this is exactly what's happening here by setting nu equals 1. So it'll do really well for high density regions, which you may or may not want. Typically, you wouldn't want that. And of course, you can do classification as well. Any questions for the moment about, novelty detection? So there's a couple of modifications. For instance, in some cases, you might want to care about relative novelty detection. So the reason is, well, let's take, for instance, this density here. By just, let's say, squishing that density region here and expanding this one here, I can make it look anything I want, right? I can apply any transform on the domain as long as it's, a diffeomorphism. And, I can make high density regions look very sparse and the other way around. Now, that sounds like completely contrived, but actually if you have something like systems logs from a server, well, nobody really has any good idea how you should represent this, right? Should you, for instance, represent the amount of data processed per machine in, number of bytes, or should you represent it in the log of the number of bytes? If you apply the log transform, then anything here gets really squished, right? So that's not entirely clear. So in that case, what you may actually want to do is something like relative novelty detection, where you say, well, you want to do well relative to another reference measure. And that will give you a slightly different type of optimization problem. You can solve it efficiently and so on. Or in some cases, you might want to have a distributed setting where you have several machines recording some data and you want to combine all of this. You have communications constraints. So all of those things will give you variance on this. What I want to at least convince you of is that if you have to do novelty detection, there's just a lot more than just fitting a Gaussian or clustering and then finding all the points that are outside those clusters. So you can do a lot better than that. Because you can design algorithms that solve specifically the problem at hand rather than some other random problem, and then you apply novelty detection to it subsequently. Okay? Any questions? Everything clear? Cool. People are very quiet. Maybe a long night after working on the homework, right? So there's coffee outside afterwards. Unfortunately, I cannot treat you to coffee right now. Now let's solve the optimization problem. So those of you who went to Moo's recitation yesterday would have already seen a little bit more about solving constrained quadratic programs. So here's the problem that you might encounter, and of course you have that in classification, regression, novelty detection, and 50 other problems. So for a small problem like 1,000 observations, you just use an off-the-shelf solver and everything's good. You could also go and solve a sequence of subproblems, and I'm going to go into that in a bit more detail and also look at primal space methods. So those subproblems are, well, since we had a quadratic program to begin with, also quadratic programs. And since they are smaller, you can use, for instance, an off-the-shelf solver for it. And then the entire question is essentially, how do you pick those subsets? The alternative is to actually go and solve the problem in primal space, in this W space. Now that is quite often not possible because, well, you're actually operating in an infinite dimensional space. But in some cases, you can make do with that even then. And so we'll look at some of those cases. So, let's say this is our quadratic program, and while the brightness levels tell us, where the optimal solution would be, so it would be somewhere down to the well, I would say the lasers, but the batteries are quite busted. Okay. Somewhere to the lower right. So yeah. Okay. So, it would be somewhere over there. Now, how do we find it? Well, let's just look back at the optimization problem, right? So this was the original problem. And what you can now do is you can simply decompose Q and A into subproblems. So let's look at this matrix Q. You can write it as, QAA, A as an active, and F as in fixed. So I have QAF, QAF transposed, and here I have QFF. Remember, those two matrices are transposes of each other because it's a symmetric matrix. And so if we have alpha transpose Q alpha, this is just, alpha A, alpha F, and here we have the same beast again. So now what you can, and you can do the same thing for the linear term, but I don't think I need to spell it out in detail. Now if you look at this, you can explicitly work out that matrix product, and you get 4 terms. You get one term that you can forget about right away. That's alpha F transpose QFF alpha F, because that's all fixed, so we don't really change it. And the rest are terms that depend on alpha A, as in the active part of alpha. Right. So what remains is that I have basically now a quadratic and the same thing happens for the constraints, that I have basically an active and a fixed part in a new subproblem. That's the one down here. And now these subproblems are small enough that I can just take my favorite off-the-shelf solver. So I could take Cplex, but Cplex is probably really expensive. Or I could take, OOQP, or you could take any other solver that you want and just, solve that subproblem. And then you update this. So by the way, if you have more homework, drop it off after the class. It's okay. You're not going to miss the deadline if you drop it off after the class. Okay, so let's say we take the subproblem here. So, in this case, well, I would have just picked out one line. And yeah, so I solve it on this line. I get some solution, maybe, get something right here. And then, I go and solve the next subproblem, and I find something around this point, and now I'm already in better shape. Okay. So this is great, but if I have, a million points, how do I select my subproblem? Okay. I hope I didn't scare him too much. He's gone. Okay, so picking those observations. If you look at it, basically, we have, all those points here that are far away. We've already solved them quite well. Here are some points on the boundary. So these are the margins. This is the decision boundary. And here, some red dots. And we know from what we did last Wednesday is that the optimality conditions need to hold. So these are the Tucker conditions. They basically say constraint times dual variable has to vanish. So now what we can simply do is we can look at our current possibly suboptimal solution and check, which of those constraints are most violated. In practice, that means just looking at those terms and looking at the biggest one. That actually tells you the current size of what's called the duality gap, as in this is the amount by which the problem and dual solution are apart from each other, because at optimality they actually match. Unfortunately, there's not enough time to go into optimization in a lot more detail in terms of what this means with duality gap. But basically, all you need to know for an operational point is that Lagrange multiplier times constraint, this needs to vanish, and the more it's violated, the more you have a chance of actually making progress. So you could basically just go and pick those guys. More specifically, if you recall, we know is that if alpha I equals 0, it means this point has to be in the green set. If it's in that range, well, we know it has to be in the yellow set. And if it equals to C, then it's among the red dots or possibly on the boundary. So we can actually determine those guys very easily. And then we just pick the ones for which this constraint is the most violated. In other words, we pick some observations for which alpha is non-zero, but which are away from the boundary. So this could have happened if we solved a problem with them before, then afterwards the solution got better, and we are actually perfectly well classifying them, or points which just happen to be not classified correctly at this point. And then we just build up a large enough set of variables. We generate the subproblem. So this is exactly what we did before, right? So we generate this problem here. And then we make a function call to our solver. So OOQP, for instance, is a nice solver. And you keep on doing this. And this, in hindsight, is like the most obvious thing to do, right? But about 10, 12 years ago, these were some of the really exciting papers in support vectors, because basically people doing support vector machines had no real clue of optimization. And so as they learned how to use optimization, they rediscovered a lot of things that are just totally obvious in optimization and wrote really important papers about it. So, morale of the story, if you're working on a new field, don't be embarrassed to publish something that is new for that field and obvious otherwise. Because you're actually contributing. In a way, the space of genuinely really novel ideas is really small. I mean, you very, very rarely have a thoroughly novel idea. Quite often it's using an existing concept in a very different way from how everybody would have thought. So it's really the standing on the shoulders of giants thing. So here are 3 strategies, and each of those at some point were quite popular. So this is what's called chunking in the support vector literature. And basically here's how it worked. This was at the time when people were doing optical character recognition, and for OCR you would expect a very small classification error, right? Because if you're doing OCR and you have an error larger than 1%, then something is seriously wrong in your system. So that meant that you also had a very small number of support vectors. So what you could do is you could basically take a first chunk of data, you solve the problem, you keep all the points which happen to be support vectors at that time, everything else you can forget about for the moment anyway. You add in some new points, you solve that larger problem, you keep on adding new points, and you keep on doing this. So at some point AT&T considered this algorithm a trade secret. Then along came some guys from the MIT, and they said, well, actually, even if some of the variables are non-zero, you can still fix them and solve the subproblem on the rest. And this was basically Ozuna and Girosi who did this. And they were the first ones to actually point out that you could do things more efficiently. And that was actually a big boom. Yeah, that convergence proof was broken, but we were all learning how to use convex optimization at the time. Then, along a couple of years later, came John Platt. He's at Microsoft, and he's one of the few nerds who actually have an Oscar. So he has an Oscar, as in Hollywood Oscar, for simulating hair, which apparently has become one of the standard ways how to simulate hair in movies. But he's also made really, so he's also responsible for something like ClearType if you have Windows and you at some point switch on the font smoothing for LCD displays. That's his idea as well. Anyway, he also came up with this thing. He's a really cool guy. So basically what he said, well, you know, what's the smallest number of variables that I need to solve, you know, a subproblem for SVMs? Well, we have one linear constraint, so how many variables do I need, at least? Do I need one? Who votes for one variable? Who votes for two variables? Who votes for three variables? More than three? No. Two is the right answer. Yep. Because I have one equality constraint, so I need at least two variables to make it still work. So he just went and said, well, let's pick pairs of variables at a time, solve the subproblem, then pick another pair and keep on doing this. And so this actually means that you can solve that quadratic program in closed form really, really cheaply. So the algorithm is very, very, very fast at making very small updates. And quite counterintuitively, it worked really well. So I never would have thought that this thing works, and it just works amazingly well. So the only problem is that it's actually quite costly to select those variables. Anyway, but this is sort of the general templates of how you can solve this. Now, there's one thing to keep in mind. So these algorithms don't just run in a vacuum. They actually work on real data, on real hardware, and those machines have real constraints. So, data comes from a disk, and you have some readings rate, it goes into memory, and you have a training rate, and it goes, goes on and on. And if you look at the, bandwidths, you can see some significant difference in numbers here, right? So your disk is really lame, memory is way faster, your cache is even faster, and then, look at those bandwidths. We're talking 3 orders of magnitude difference here. And yeah, sure you can find faster disks, and sure you can find faster SSDs, and you can have many memory chips in your machine. So, yes, you can get bigger numbers than that, but these are sort of, ballpark typical numbers. The orders of magnitude difference still remains. Now, what this means is that if we just go read data from disk, do one update on it, and then, throw it away again, this is extremely stupid. It's extremely stupid because basically our CPU will just sit idle most of the time, and you may have heard, if you listen to any big data talk, that all those algorithms are bandwidth constrained, right? They'll tell you that, well, the main constraint is the disk, the main constraint is the network, yada, 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 and it doesn't really matter how fast your processor is. Well, actually what they just told you is, I've designed a very stupid algorithm that doesn't use the processor, and I have no idea how to fix it. Right. Okay, you can quote me for that. Yeah, so the thing is that you just have to then think, well, now that I've already got the data in memory, well, can I do something else that's useful with it, rather than just throwing it away again and letting the CPU sit idle? And as a matter of fact, you can. You can just reuse the data several times over and over for further updates. And you just have to be smart about making it happen in such a way that it doesn't just overcount that observation, right? Because if you just do an update and you see the same instance 10 times, that shouldn't behave in such a way as if you had seen that instance 10 times. So the way we implemented it is basically, well, that's why it's called dual cached loops in that paper. You have one read loop from disk into memory, and it basically writes into a ring buffer. Let me draw the picture. So here's the disk, here's a ring buffer, and there's a thread that keeps on writing into that ring buffer. And that may be, if you have like 16 gigabytes of memory or whatever, it'll take a while to fill it up and keep on writing. I have another thread, so this is disk, here's CPU, and here's, whatever workspace that it operates on. These are my coefficients. And it reads from that ring buffer, except that it goes around much faster, right? Because my memory bandwidth is, 30 gigabytes a second. So this goes around in about half a second here. Then the disk is writing at 150 megabytes per second, right? So this takes about 100 seconds. So in other words, the CPU can touch that data, if it's just a matter of memory bandwidth, 200 times before I end up throwing it out. Now, you don't bother about those things if you get a speed of a factor of 5. You do care if you just beat everybody else, and that's basically what we did. So the fun thing here is, so this is our algorithm, and it basically converged to a good enough solution. Now, this time, and that's just time. Now, the interesting thing is, the fastest competitor took that long just to prepare its internal data structures. By the time it's prepared its data structures, we are done. So and that fastest competitor got the best paper prize for being such an amazingly fast algorithm the previous year. So, yeah, basically, know your hardware, and you get drastic performance improvements by just, being smart about using resources in the right way. And that's not just hackery, because sometimes those constraints are quite systemic. So you need to design algorithms that actually exploit this, because that problem is not going to go away with a different generation of hardware. Okay. Now, any questions about that so far?
So can you tell us more about how we pick the pairs in the SMO?
Okay. So picking the pairs in SMO, that's a very good question, right? So basically, you want to pick essentially, so the ideal situation is you have one point that actually sits over here and has an alpha equals 0, and you have another point that sits over here and has an alpha that's greater than 0. So in other words, you have 2 points which actually should just trade places, and that's, for instance, one of the points that you pick. Now, that would require, a double for loop just to select the right point, which isn't very smart. So first of all, you would actually go and cache those values, such that, when you update your parameters, you only have to do a small number of updates. Or you may actually be smart in how to cache it. And there's a lot of tricks on how to make this go fast, because in some cases, you can reasonably quickly just decide, well, these points are not really relevant. So you might have an auxiliary data structure, like a KD tree or a cover tree or a core set, to tell you which points you probably can forget about. And so you very quickly want to narrow down your search strategy for looking at suitable pairs to subsets that are most promising. And you can do a lot of engineering in there. Every couple of years, somebody else comes along with a really amazing idea in that context. By now, I would probably look at core sets and essentially, have compact representations for, small subgroups, and just eliminate subgroups right away very quickly. Actually, right now, I would probably use a primal space algorithm and use something called fast food, but that's a different story. So this is still in preparation right now, so it's due next week. Yeah. So let me therefore tell you a little bit about primal space methods. But this was a good question. Any other questions about selecting variables? No. Okay, good. So let's look at gradient descent for a moment. I mean, this is about the dumbest algorithm you can find, right? So I have, some objective function. That's my loss, that's my regularizer, go and compute the gradient, and then I just take a gradient descent step. And that picture shows quite nicely how things can go badly wrong, because you want to go from here to there, except that it keeps on zigzagging around because, well, the space is distorted and stuff just goes wrong. Okay. Now, of course, you can fix that by just fixing, that space by undistorting it. And conjugate gradients, for instance, is a fantastic algorithm which will do that. It basically performs Gram-Schmidt orthogonalization on the gradients as you go along. And this works even for non-quadratic functions. Just for general convex functions, you just take a few conjugate gradient steps, and possibly at that point you reset again. There are other variants like BFGS, which you should definitely look at, and you should never implement yourself. And then there is versions like LBFGS, there's a version OBFGS, and there's a version OLBFGS. Okay, so BFGS, I think Broyden, Fleischer, Goldfarb, and Shano, and I may have butchered some of the names, is even after probably about 2 decades, still one of the best non-convex solvers that there are. And there are lots of variants on that. Essentially, the idea is it makes a quadratic approximation of the problem that you're solving, and it keeps on updating that quadratic approximation. The L part comes from the fact that if I have a high-dimensional problem, the quadratic approximation is super expensive, so it uses a memory-limited version. The O comes from online, and then there's an online memory-limited version, and basically those algorithms are actually quite nice. So, given that there are a myriad ways of screwing up and making them very inefficient, and there's a lot of hand tuning and being very smart about things, use existing implementations. Avoid implementing them yourself. It's really important that you only implement them yourself as a last resort, because it'll probably not be as fast. And you wouldn't believe how many people actually implemented it, and then you just use a library call instead, and it goes faster. Okay, so back to gradient descent. So this is like really stupid if we have those canyons, and real data tends to have this property. But what's even worse, or at least as bad, is, well, suppose that a lot of the observations that I take, let's say I have lots of handwritten digits, and I, give you a lot of digits that look almost the same, right? And this is really wasteful because all those loss gradients will look exactly the same. As a matter of fact, I can be really mean to you, and I give you the data set, and by some mistake I made 10 copies of it, and I scramble it up, and you get 10 times the data. All of a sudden your work has just become 10 times as large, unless you realize that you have 10 copies, identical copies of the data. So what can you do with it? Well, actually the point is to not really look at everything at the same time, but only look at one result at a time. So think of it like if you have a textbook that's super redundant and keeps on going over the same stuff over and over and over again. You'll probably just start learning by reading through a few pages, and at some point you just chuck it back on the shelf. So here's the empirical risk, right? And the stochastic gradient is actually the algorithm is very simple. All you do is you just take one loss function at a time, you compute its gradient, and you take a teeny step in that direction, and you update. And quite often, you might require that those parameters are in some set, so you update and then you project back. So let me show you what this means in pictures. Let's say this is my convex set. Here's my parameter. Here's an update. So it takes me out here. And then I project back. So this is now the new update. And there are lots of ways how you can project, but typically, least mean squares, so the L2 projection is a very reasonable thing to do. And yes, you can write lots of papers about clever projections. Just as a refresher, so this is redundancy in the sense of, where online learning is smarter. So here are some loss functions, and you've probably seen all of them so far, right? We've seen soft margin, we've seen the logistic, quadratic, L1, L2, Hooper, novelty detection. We've seen all of those, and there's lots more. So this works for all of those cases. And the good thing is that this very simple algorithm that I just showed you actually has nice convergence properties, and I will spare you the proof, unless you should very strongly desire to see it. You can go through it in the slides. Okay, and if you have strong convexity, you can get even better guarantees. So there's a lot of math on the slides. It's reasonably compressed relative to what you can do. So by the way, strong convexity means that, well, let's take a function that's convex. Okay, 2 points, and yeah, that's fine. Now, so in other words, what I have is that f of x lambda f of x plus 1 minus lambda x prime is greater or equal to f of lambda x plus Now, strong convexity says that this has to hold with this plus a small quadratic term. That's it. So basically, you can even put the parabola. So this is, for instance, the case for L2 penalties, where I have this additional w squared part, right? So where I have this plus parabola. So of course, that is immediately strongly convex. And that gives me faster rates. It basically means the problem is a lot simpler. Now, let's talk about regularization a little bit. And yeah, I mean, there'll be more deep. I mean, for your benefit, all these stochastic gradient descent algorithms, you only need to be able to use them and look through the proofs if you feel like it. Essentially, the nicer, the smoother the problem is, the faster usually the rates. And depending on how you set it up, you'll be able to, benefit from the smoothness properties of the problem, even if you didn't know it beforehand. Okay. So given that you guys all voted for regularization, okay, let's look at that. So for, probably about 10 years, people were running around saying that the SVMs work because they map the data into this high-dimensional feature space and they just solve the problem there. But that kind of, flies in the face of all the statistics wisdom, because, the higher dimensionality, the more data you need. And, well, it basically just cannot possibly be true, right? So the worrying issue is that, some kernels really map into an infinite dimensional space, like the Gaussian RBF kernel. And that's actually one of the more popular ones anyway. But the other thing is those kernels actually work well in practice. So, how do we reconcile this with infinite dimensional space? We know that this is a bad idea in general, but somehow it works. Well, the reason actually why it works is because, there are margins. And by solving the large margin problem, what you're effectively doing is you're not just solving only a straightforward risk minimization problem like here, but we also have the penalty. So this is a regularizer. And remember, this was like, this 1/2 w squared. One thing that I did is I put the lambda here, and sometimes you would have like a coefficient c up there. But obviously, these are equivalent. So for each lambda, there's a c. Right? And we saw those loss functions. Okay. And so this is exactly that transformation that I alluded to. Whether you have this coefficient c here or whether you have this coefficient lambda there, these two are really equivalent. Right? Now, what we really want is, we want that, the functions that we are getting to solve the problem, that they are simple. So for instance, they should be smooth, they shouldn't, wiggle too much, they shouldn't have very large values. Remember in the first lecture, when I showed you how this polynomial regression went badly wrong, you could see that this function just had ridiculously large values. And that's exactly the thing that we want to control. So let's do that, right? So one thing that you could, for instance, say is, well, I want to have a function that has very small derivatives. So, or I could say I want to have a function that has, small function values. Or maybe I want to have a function that has a small second derivative. So you can, just mix and match and pick and choose. And so you get, some criterion for what constitutes a nice function for you. Okay, so you get some omega of f. So far, this doesn't really look like kernels at all, but this is just some way of quantifying whether a function is simple. Okay. And so what I'm going to show you is that this actually can be mapped reasonably cleanly into kernel land. So the first thing to do is to look at this regularization operator, omega of f. So remember, for instance, I might have something like the integral of f squared of x plus dx f of x norm squared plus, and then, suitable norm d squared of x, f of x, dx, right? And this might, now I can write this as basically the inner product between, identity dx d squared x applied to f, and the same thing again applied to f. This is now, a high dimensional vector. So let me call this operator here p. So this is, in other words, nothing else than pf dot pf in a slightly different space from what we had up here. And, well, without loss of generality, if I have, f being some linear expansion, so in other words, f being some over alpha I fi, then I can just plug that in here, exploit bilinearity, and I get that this is sum over alpha I, alpha j, and then here we have pfi, pfj. And this is what was proposed, for instance, in the context of regularization networks. So people like Federico Girosi, or also Tommy Poggio, they published a lot of really cool papers in that context. So now if you squint at that, it looks very much, this expression here, it looks very much like our kernel expression, right? So with kernels we had a k of xi and xj, but here we have a p of fi and p of fj. What if we could make this work out nicely with kernels? And that's essentially the idea of building that connection. And remember we had, the norm of w squared is alpha I, alpha j, k of xi, xj. So let's just find, a matching pair of p's and k's such that k of x and x prime is p applied to k of x and dot, and p applied to k of x prime and dot. Now it turns out that Green's functions will do precisely that for you. So if you've done physics, you'll know that Green's functions are a way of inverting operators. And basically all I'm saying is, so by the way, P star is the adjoint, so this is like, in operator speak, the transpose of the matrix. So we have operator transpose times operator, this beast applied to K. And if that holds, that P star P applied to K, inner product with f is f of x, then in particular, this equality will also hold. If I can satisfy this, this is a no-brainer, because I can just pull P over, so I get P star P, K of x and dot, applied to K of x prime and dot. Now I'm evaluating this at x, that's exactly the reproducing property, and so I will get K of x and x prime. So, a lot of details aside, turns out that, this is exactly how you can match up regularization operators in kernels. And so, if I have some measure of smoothness, as soon as I can, for that measure of smoothness, guess or figure out in some other ways k, I'm in business. Let's just skip that. Let's look at one specific case. And this is actually probably the most relevant one here for us anyway. So let's say, for instance, I want to have a function that is, smooth, that has small values and that is smooth. Okay. So this is our regularization operator. That's basically PF inner product with PF. I can write this as, this integral. Now we know that this integral has to be the same in Fourier domain. And the reason why I went into Fourier domain is because in Fourier domain, well, derivatives are just multiplications. So I have f Fourier transform of f of omega squared plus omega squared again this beast. So I can write this as the Fourier transform of f squared divided by some p of omega, where this p of omega is just this function here. Right. So this actually works in general. So it works whenever you have a kernel that is translation invariant, or whenever you have an operator where by shifting the function, the value of the regularization function doesn't change. In other words, if my function is smooth here, it's just as well if the function is smooth there. And so in general, you get these expressions here. And the good thing is once you have that, guessing the kernel is really easy, because actually it's the inverse Fourier transform of this object. So if you work it out, you'll see that exactly that type of kernel will satisfy the conditions. Now, what does it mean intuitively? It means that, whenever this quantity here is really large, well, that's where you really care about the function value a lot. Wherever it's small, you care about it very little. In other words, if this p of omega, let's make omega really large, right? These are very, very rapidly varying functions. So p of omega goes to 0. 1 over p of omega gets really large, so we penalize it a lot. So think of this like, a frequency filter that you apply to your functions. And in order for the frequency filter to work, you need to penalize a lot if you have, very wiggly functions or functions that are otherwise not exactly how you want them. And you don't necessarily have to have this very simple polynomial form. You can just stick anything in here. And then as soon as you take a Fourier transform, you're back in business. And of course, this kernel is translation invariant. That's just how it's engineered. So everything's good. Let me show you a few examples. So this is exactly the smoothness constraint, right? 1 plus omega squared inverse. In the Fourier transform, that just gives you the Laplace kernel, this object. For a Gaussian, well, actually the Fourier transform of a Gauss is a Gauss, so we already know that if this is our smoothness, then this is the kernel. And so you can see if, that smoothness condition decays very rapidly, you're basically going to get a lot of very low frequency functions. Okay. And yeah, you can do a similar thing for polynomials, and I think we will skip over that because that's way too technical. Unless you particularly enjoy Legendre decompositions of polynomials, which I don't think anybody here does. Any questions so far? Okay. Let's look at something a little bit more practical, so you're not going to entirely escape the string kernels and hashing. Okay, so let's just look at what people used to do with text. The reason for actually going through that in a bit of detail is because text is quite likely one of the key applications that you're going to encounter when you use, a generalized linear method or an SVM or something like that. So, the earliest version was basically bag of words, and I'm aware of it at least from '95 at AT&T, and that is actually still close to state of the art in many large internet applications where people use a fancy version of a bag of words. And yes, you can do smarter than that, and I would have to kill you if I told you. But yes, bag of words gets you fairly far if you weigh things properly. So what is bag of words? It basically means that, well, just this slide, and I take a text and I just count how many times each word occurs. And so to be or not to be is garbled into this vector here, which completely, obfuscates all the meaning that was in there, but it might still give you a pretty good idea of, what this text is about. You can do smarter things than that. So in bioinformatics, just matching substrings is really good. Then some folks also in bioinformatics came up with the idea that you can actually, also use approximate matches and so on, and come up with a very clever way to compute it. Then we came up with a very computationally efficient version that, was linear time, which was very cool, except that it used way too much memory. Then Vichy and Chunhui fixed that, but it was still not very efficient. And I'll show you something that's actually much more effective than that. And then there's something like rational kernels, which, if you like weighted automata and graph transducers, is an awesome and cool thing. If you don't like them, you will not enjoy reading the paper quite as much. But it's very cool math in there. So, bag of words, very simple idea. The inside of Thorsten Joachims then was, hey, these are actually sparse vectors, so let's just code them up sparsely. So, mind you, by now you get questions like that in a job interview at Facebook. Take the inner product between two vectors. How can you do it efficiently if the vectors are sparse? I hope they don't ask this question anymore now, but if they do, you have an edge. Then, Patrick Hafner realized that you can use in an inverted index, so that way you can, if you only have a small number of matches, go through that even more efficiently. And then you can do all sorts of clever reweightings and TF, IDF, and basically your friendly NLP colleagues would tell you a lot of really cool tricks on how to do this. Okay. Substring mismatching, so this is basically the pair HMM that I mentioned before a couple of lectures ago. So the idea is that you want to check whether two biological sequences, let's say, might have a common ancestor. So you say, well, I have a common ancestor. Now let's see how these can evolve by emitting one or another sequence. And if you write it as such a pair HMM, which looks like a Michelin man who's fallen over, so you can grok all that in detail later. But basically, in some cases, you can do this computation very efficiently if you know dynamic programming. And we'll get to dynamic programming eventually in this class. You can look at substrings. This is actually really good if you need to do sequence assembly, and you basically say, well, two sequences are similar. If their subsequences are similar, this is very, very fast. Or you can look at entire suffix trees, and basically, if you've never heard of suffix trees before, so that's actually a very nice piece of literature. So, well, try reading a understandable version of Ukkonen's paper. Okay. The point is, this doesn't actually solve all the problems that we have, because you might have a monstrous vocabulary size. So you might have like 100 million different tokens easily, maybe 1 billion. You would have to possibly build a dictionary such that you map each of those tokens into a position in your sparse vector. The approximate matches are still an issue, and the suffix trees, well, you need actually a lot of bytes per character, so it doesn't really help you. And quite often you need to keep everything in memory. The reason for that is because, well, if you receive a spam email and you have to hit the disk, whenever you receive a new spam email, then you can service about 20 emails per second per disk. With SSDs, that's not quite as bad anymore, but if you basically have to hit the disk for a lot of lookups, well, forget it. On top of that, these algorithms are actually really difficult to implement. So what I'm going to show you now is something that actually works at least as well as all those things, and is ridiculously simple to implement. So for that, let's just also cover something called multitask learning. So that's a small side note. You'll also learn a new machine learning problem on top of everything else. So, once upon a time, basically people would receive emails at Yahoo, and then they would get this email, and they might actually label it. Mind you, this is actually the silent majority. Most people just don't label their stuff. But you get all sorts of other things in between. So one way to solve this is to say, well, each of them gets their own classifier, but that's kind of not so great, because if each of them gets their own classifier, then, well, this user here is screwed, right? They don't label any data, so I can't really build a classifier. So the idea is to actually have a global classifier and then say, well, everybody gets a small correction relative to that global classifier. Now, here's what really happens. So let's go back to the document camera. So let's say I want to compute f of x for a given user u. Well, that's basically the global part. So I have, let's just take phi of x for inner product with w. That's the global. And then I add to that phi of x inner product with w for that user. You can already see where this is going, right? Because, let's say we have a smallish vocabulary size of maybe 1 million. So phi of x is in r to the 10 to the 6. That's a small vocabulary for spam filtering. But it's better? Okay, sorry. The camera doesn't have a very good depth of field. Yeah, so now the problem is I might have maybe 1 million users. So these are small numbers. I mean, most spam filter systems might have more than 1 million users. So unfortunately, I now end up with 10 to the 12 parameters. So if you take Facebook, you make that a 9. If you have a heuristic spam filtering system, you make that maybe an 8. So in other words, this might very well go to 10 to the 17. This is extremely bad news. Now, how do we actually fit all of that into memory? Right? So obviously there's no way you can fit all of that into memory exactly. But it turns out that since most users only receive emails that contain some words and not a lot of others, you can actually make it fit by just by doing exactly what you would do also if you had an array. You would hash things. And occasionally stuff will collide and then you have to do something about the collision. And we pretty much do the same thing, except that we don't do anything about the collision. And nonetheless, you can actually show that this is not as crazy as it seems. So the first thing is to actually write this entire thing out as an inner product in its own right. So I can write this out as phi of x tensor product with 1 and EU. So that's the unit vector for that particular user. Right, so if this were 10 to the 6, this is basically 1,000,001 dimensions. And this is still, 1 million dimensions. And now I have a different W. Not to make it consistent. Okay, so I haven't actually changed the problem, but at least now we've made the multitask learning part go away. Mind you, this has actually been done before, so people have taken products of kernels before. And there's this cool paper by Hal Daum on embarrassingly simple multitask learning. and he shows how to solve 4 or 3 tasks at the same time. Unfortunately, we have 1 million tasks here. So, depending on how you count, I mean, you end up with this idiotic amount of space. So, hashing to the rescue. Here's what happens. Yeah. Basically, you get this email and you would do the bag of words. And since you want to do the multitask part, you have the word. And you also have the task, let's say the user. And so Barney gets his own parameter, right, for the word mention. And so you actually have to do a dictionary lookup because, say, Barney and mention goes to this position here, and you get the count of 1. So, and then the idea, if I have this sparse vector, which is now in an infeasibly high dimensional space, I take a hash function to map it into a low dimensional space. And what this hash function does is actually something extremely simple. I have one big fat matrix. Actually, that matrix has almost no non-zero entries. It's all zeros except that for a given row, we have all zeros except for 1, 1 or a minus 1. So we have a plus minus 1 here, and the rest is all zeros. Sorry, it's actually, the matrix is short and fat, not tall and sweet. And the rest is all zeros here. So as we now multiply with this very high dimensional vector, it maps into a low dimensional space. And the position where the 1 is will depend on a hash, and the sign will also depend on the hash. And I'll show you in a moment. So here's what we do. We basically compute, and the good thing is, well, we can actually throw away the dictionary. We just compute the hash of the word, because, I mean, it would be kind of stupid to look up the word in the dictionary, get some token out of it, and then hash that token. Well, we might as well just hash the word directly. And this tells us where in this vector stuff goes. And then we take a 1-bit hash, which is basically going to be 1 or minus 1, and multiply it accordingly. Okay. Who knows what a hash function is? Who hasn't seen a hash function before? Okay. And the rest is asleep. Good. So, hash functions work as follows. Does everybody know what a random number generator is? Okay, good. So a random number generator has this effect that you usually have this function called, it's called seed. And you seed it with some x. And then you have, z is rand. Right. Okay. So this random seed makes sure that, we always get the same sequence of random numbers back. And so if you've never seen a hash function before, then I could make this entire thing a function call which is hash of x. Okay, now basically what it does is it generates a random number in such a way that you can look it up again if you feed it the same key again. Now there are all sorts of really nice properties about hash functions, how independent they are. So typically you want to make sure that if you feed in 2 different x's, the numbers that you get are essentially as good as random. Basically think of this as a mechanism of generating random numbers and not having to store them ever again. You can always recompute them. And the good thing is those hash functions are really fast, and the one that you should probably look at is murmur hash. And there's, I think, murmur hash 3 out now, and that's about the fastest you can find. Anyway, so that's, for the purpose of this, what a hash function is. The only thing that I'm going to do is I'm going to limit the number of digits that I look at, because it needs to actually map into something that fits into memory. Right? So this has to fit into memory. This one didn't. And so, while you basically don't need a dictionary anymore, This makes it really easy. You save a lot of work. You can just start processing the data, whereas everybody else will be building their dictionary first. You're already working on the problem. It fits into memory, and, well, you basically get all those nice things. It implicitly maps into this high-dimensional space. This is all really nice. Now, you can prove, and we're not going to go into detail, that orthogonality is approximately preserved. So if I have two vectors that were orthogonal before, then with high probability, they are still orthogonal. You can get that through basically a Chernoff bound. And you can also show that in expectation overall, the hash functions, the inner products are preserved, and you can work out the variance. So this is actually all quite nice. But the proof is in the pudding. Here's what you get. Basically, if you know, this is a tiny problem, like this is 20 million emails and 400,000 users. But yeah, that was, small enough that Yahoo considered it sufficiently relevant that we could actually publish things about it. And the black thing is a baseline of, one whatever number of units of spam. And so you can see that the personalized spam filter, does better than the hashed one. And even if you only have, a fairly small range for, the size of the hash function. So 22 basically means a full many-dimensional space, because it's 2 to the 22. That means a 2 to the 26 dimensional space. So the problem, however, is there are lots of users that don't label stuff. When was the last time you labeled an email as spam? Who labeled his email as spam today? Last week? Last month? Okay. Guys, you're way out here. So here's what happens. And this is one of the nice things of multitask learning. So this is basically if you evaluate the errors based on how many labels you get. And well, those who label most of the emails benefit the most. Those who label very little will benefit less, but they still benefit. That was actually the really nice and surprising thing. So the reason why this works is basically just because, well, some users have very peculiar and abnormal ideas of what constitutes a relevant email. Remember, you might even have spammers who mislabel things. So they therefore, will get, a spam filter that suits their needs quite well, and they will see their own spam emails going through, but nobody else does. Does somebody still remember what kill files on news forums are? So how to deal with a troll on a news forum? Everybody knows what a troll is, right? Okay, people writing stupid posts. Now, usually when you get somebody like that and, well, you want to get rid of them, well, you can block their account, but that doesn't really work because they'll just create a new one. Right? It's just a whack-a-mole, so it doesn't work. And usually they post inflammatory stuff and people respond and there's a flame war, and that's not always a good thing. It's actually good for advertising, but it's a different story. So what you do instead is you set it up in such a way that only the troll sees his own posts and nobody else does. And that way the troll sees, okay, I posted this thing, everybody therefore has to see it, and nobody likes or is responding to it, and at some point the troll just goes away. At least the not so smart ones, and that correlates well with trolls. So effectively, this builds a similar thing for spam, right? Because the spammers who mislabel a lot of their spam as ham, well, we'll see that their spam goes through. So it also makes it harder for them to check how good the spam filter is. No, we won't have time for details. There's a lot of clever things you can do in terms of, how to be clever about memory, layouts, and so on, but not in this class. So I'll put the slides up online, and you can, read it up there. There's cool things about column rulers, but yeah, that's it for today. Could you please press the stop button on the camera?
Thank you.